A patient has a heart attack. The cardiologist rushes to restore blood flow, opens the artery, reperfuses the myocardium. The ischemia is over, but the tissue damage doesn't stop. It accelerates. More cells die after the blood comes back than die during the blockage itself. That's not a mistake. That's reperfusion injury, and the weapon is oxygen. The same molecule keeping you alive is the one burning the tissue down. Here's the mechanism. Before we get to reperfusion, we need a 30-second primer on free radicals. A free radical is any molecule with an unpaired electron in its outer shell. That unpaired electron makes the molecule extremely reactive. It wants to steal an electron from a neighboring molecule. When it does, that molecule becomes a radical, steals from the next one, and you get a chain reaction of cellular destruction. In medicine, the most important free radicals are reactive oxygen species, or ROS. There are three you need to know. Superoxide, written O2-, is the primary ROS and the precursor to the others. Hydrogen peroxide, H2O2, is less reactive by itself, but becomes dangerous in the presence of iron. And the hydroxyl radical, OH-, is the most dangerous of all. It directly attacks membranes and DNA. On exams, hydroxyl radical is the favorite. Now, where do these free radicals come from? There are 4 sources, and each one maps cleanly to a different exam vignette. Source 1 is normal oxidative phosphorylation. In mitochondria, oxygen normally accepts 4 electrons to become water. That's how ATP is made. But occasionally, 1 or 2 electrons leak out early and react directly with oxygen, forming superoxide. This happens all the time. Your body produces free radicals just by being alive. That's why antioxidant defenses exist at baseline. Source 2 is NADPH oxidase, the intentional source. Neutrophils deliberately generate ROS to kill bacteria. During phagocytosis, NADPH oxidase converts oxygen into superoxide. That superoxide becomes hydrogen peroxide, which myeloperoxidase then converts into hypochlorous acid, essentially bleach, to destroy the pathogen. The disease that lives here is chronic granulomatous disease, CGD. It's an X-linked recessive deficiency of NADPH oxidase. Neutrophils can engulf bacteria but cannot kill them because there's no oxidative burst. The classic vignette is a young boy with recurrent staph and aspergillus infections and a negative NBT test. Diagnosis is NADPH oxidase deficiency. The reason catalase-positive organisms matter is that they destroy their own hydrogen peroxide, leaving the CGD neutrophil with nothing to use. Trap 2 is acetaminophen overdose. The mechanism is CYP450 conversion to NAPQI, depletion of glutathione, and direct hepatocyte damage. The treatment is N-acetylcysteine, which replenishes glutathione. Now we're ready for the centerpiece, the mechanism of reperfusion injury and why it's counterintuitive. During ischemia, while the artery is blocked and oxygen is absent, the cell doesn't just sit quietly. It's working hard under anaerobic conditions, breaking down ATP desperately for energy. ATP degrades step by step. ATP to ADP, to AMP, to adenosine, to isoleucine, to hypoxanthine. Hypoxanthine accumulates inside the ischemic cell. At the same time, ATP-dependent ion pumps fail. Intracellular calcium rises. That calcium activates a protease called calpain. Calpain converts xanthine dihydrogenase, a normal enzyme, into xanthine oxidase, the dangerous form. These are 2 forms of the same enzyme. Here's the key difference. Xanthine dihydrogenase uses NAD+ as its electron acceptor. Xanthine oxidase uses molecular oxygen. During ischemia, there is no oxygen. So even though hypoxanthine is accumulating and xanthine oxidase is being generated, nothing happens yet. The enzyme is loaded, the substrate is loaded, but without oxygen, no damage. Yet. Then the cardiologist opens the artery. Oxygen floods back in. Now xanthine oxidase is active and it has a massive stockpile of hypoxanthine sitting there from the entire ischemic period. XO converts hypoxanthine to uric acid, and as it does, it dumps electrons directly onto oxygen, producing a sudden burst of superoxide. Superoxide becomes hydrogen peroxide. Hydrogen peroxide meets iron through the Fenton reaction and generates hydroxyl radical, the most destructive species. In the first few minutes of reperfusion, there is a storm of ROS generation that overwhelms antioxidant defenses. That's why tissue damage can be worse after reperfusion than during ischemia itself. Ischemia set the trap. Reperfusion pulled the trigger. What do these free radicals actually damage? There are 3 targets, and each one is tested differently. Target 1 is membrane lipids through lipid peroxidation. Hydroxyl radical attacks polyunsaturated fatty acids in cell membranes. It steals a hydrogen atom, creating a lipid radical, which reacts with oxygen and attacks the next lipid. This chain reaction destroys membrane integrity. Cells swell, organelles rupture. This is the primary mechanism of cell death in carbon tetrachloride toxicity and in reperfusion injury. Target 2 is proteins. Free radicals oxidize amino acid side chains, cross-link proteins, and fragment polypeptide chains. Enzymes lose function, structural proteins break down, the cell loses internal regulation. Target 3 is DNA. Free radicals cause single and double-strand breaks. They oxidize bases, especially guanine, forming 8-oxyguanine, which leads to G to T transversions during replication. This is a direct link between free radical damage and carcinogenesis, and it shows up on exams. The body isn't defenseless. There are layered antioxidant systems that intercept ROS at every step. First, enzymatic defenses. Superoxide dismutase converts superoxide into hydrogen peroxide. There are 2 main forms, copper-zinc superoxide dismutase in the cytoplasm and manganese superoxide dismutase in mitochondria. Catalase converts hydrogen peroxide into water and oxygen. It's located in peroxisomes and prevents H2O2 from becoming hydroxyl radical. Glutathione peroxidase also neutralizes hydrogen peroxide and lipid peroxides, using reduced glutathione as the electron donor. When glutathione is depleted, as in acetaminophen overdose, this defense fails. Second, non-enzymatic antioxidants, vitamins A, C, and E. Remember ACE, like the playing card. Vitamin E is the most important for membranes because it's fat-soluble and sits directly in lipid bilayers, breaking lipid peroxidation chains. Drug connections matter. N-acetylcysteine is not an antioxidant itself. It provides cysteine so the cell can regenerate glutathione. That's why it treats acetaminophen overdose. And allopurinol inhibits xanthine oxidase, blocking the initial superoxide burst during reperfusion. Now let's lock this into exam performance with 4 vignette traps. Trap 1, CGD. A young boy with recurrent staph and aspergillus infections and a negative NBT test. Diagnosis is NADPH oxidase deficiency. The reason catalase-positive organisms matter is that they destroy their own hydrogen peroxide, leaving the CGD neutrophil with nothing to use. Trap 2 is acetaminophen overdose. The mechanism is CYP450 conversion to NAPQI, depletion of glutathione, and direct hepatocyte damage. The treatment is N-acetylcysteine, which replenishes glutathione. Now let's lock this into exam performance with 4 vignette traps. Trap 1, CGD. A young boy with recurrent staph and aspergillus infections and a negative NBT test. Diagnosis is NADPH oxidase deficiency. The reason catalase-positive organisms matter is that they destroy their own hydrogen peroxide, leaving the CGD neutrophil with nothing to use. Trap 2 is acetaminophen overdose. The mechanism is CYP450 conversion to NAPQI, depletion of glutathione, and direct hepatocyte damage. The treatment is N-acetylcysteine, which replenishes glutathione. Now let's lock this into exam performance with 4 vignette traps. Trap 1, CGD. A young boy with recurrent staph and aspergillus infections and a negative NBT test. Diagnosis is NADPH oxidase deficiency. The reason catalase-positive organisms matter is that they destroy their own hydrogen peroxide, leaving the CGD neutrophil with nothing to use. Trap 2 is acetaminophen overdose. The mechanism is CYP450 conversion to NAPQI, depletion of glutathione, and direct hepatocyte damage. The treatment is N-acetylcysteine, which replenishes glutathione. Now let's lock this into exam performance with 4 vignette traps. Trap 1, CGD. A young boy with recurrent staph and aspergillus infections and a negative NBT test. Diagnosis is NADPH oxidase deficiency. The reason catalase-positive organisms matter is that they destroy their own hydrogen peroxide, leaving the CGD neutrophil with nothing to use. Trap 2 is acetaminophen overdose. The mechanism is CYP450 conversion to NAPQI, depletion of glutathione, and direct hepatocyte damage. The treatment is N-acetylcysteine, which replenishes glutathione. Now let's lock this into exam performance with